dissertation to. Thank you. Perfect. So today I'll be talking about using compact stellar systems as, by which I mean globular clusters and ultra-compact dwarfs, as tracers of how galaxies are affected, how galaxies evolve, and how they're affected in dense cluster environments. Let's get the technology sorted out first. There we go. So I'd like to start by thanking my supervisor and committee members for their support throughout this project. In this defence today, I'll be basically splitting it into four sections. So I'll start by outlining the motivation for this thesis, and then introducing the two main protagonists, the Coma Cluster and compact stellar systems. And then I'll be summarising the three papers that I've actually produced as part of this work, part of this project, before bringing it together in a discussion and conclusion section at the end. So the history of astronomy is a history of receding horizons, so said Edwin Hubble in his 1936 book, The Realm of Nebula. Galaxy evolution is a part of that expanding horizon, and it asks how the universe built the environments in which stars, planets, and eventually life became possible. But galaxies don't evolve in isolation. They're shaped by their surroundings. And today, some of the densest and most extreme galactic environments that we know of are galaxy clusters. So the question then becomes, this is the central question of this thesis, it's how do galaxies evolve in a cluster environment? So this is a big question, and to make it more manageable, to break it down, this thesis uses three ideas. So I'm going to study the dense environment of the Coma Cluster. I'm going to ask how the environment affects those member galaxies, and I'm going to use compact stellar systems as long-lived tracers of the environmental processing within that cluster environment. But first, so if you were given this as a snapshot of a population, what could we infer? What could you infer from this snapshot? So if this was the only image that we had, we could look at, say, population sizes, we could look at ages, we could infer motion perhaps of the bipedal beings that you're standing on. Some of them are standing on one leg. We wouldn't be watching a life unfold. We wouldn't be watching a life cycle of these individual people, but the population would still contain clues to its history. So what's the point of this analogy? Well, we have exactly the same problem with galaxy evolution. We can't watch a single galaxy evolve over billions of years. So we mostly get snapshots, but the populations actually encode histories. So the question then becomes, what can we read from this snapshot? So there are many possible observational clues that we can infer from the details that we get. And I stress that this is not an exhaustive list, but we can look at morphology, so we can look at the shapes, the sizes, we can look at the colors of the objects, we can look at tidal features where there's been interactions. We can look at the diffuse stellar light. We can look at the local density environment, characteristics of the local environment, and then we can look at the compact stellar systems shown down in this corner. And my thesis focuses on this final class of tracers, the compact stellar systems. So because they're dense, they're long-lived, and can preserve evidence of interactions even when the galaxy itself has been reshaped. So compact stellar systems include globular clusters and ultra-compact dwarfs. So globular clusters range in size from nominally 1 to 10 parsecs, and UCDs range in size from 10 to 100 parsecs. So parsec is about 3.2 light years for something which people non-astronomers may relate to a bit more. So there's small, dense stellar systems, and many are among the oldest stellar systems in the universe. And just to point out, because it becomes important later on, all the stars that you can see here in this image of Messier 54 from the Hubble Space Telescope, these are, you can see the individual points of light. So those are stars which are resolved for one of the closest globular clusters to the Milky Way. Looking at the Coma Cluster, which is very much further away, as I'll go to in detail in a minute, we only get the integrated light from those from all of those stars, and they resolved as point sources. So we'll come across that again in a minute. But remember that picture. So because these globular clusters are long-lived, we can take their numbers, their colours, and their spatial distributions to act as a fossil record of the assembly and the environmental processing of their host galaxies. So as we see from, they're also ubiquitous in the halos of galaxies. And as you can see from this image, that would have been something that Harlow Shapley would have dreamed of when he was positioning, seeing the view of the globular clusters around the Milky Way. So this is the distribution of globular clusters, which is what he used to determine that the sun wasn't the center of the Milky Way back in 1922, something like that. So the other protagonist is the Coma Cluster. It's located in the constellation Coma Berenices, the Hare of Berenice, and as shown here, it is historically important from its early identification as a cluster to Futzwicky's dark matter argument, but it's also observationally ideal for this project. Because Coma is one of the nearest and truly dense clusters. It's a massive cluster. It's over 100 megaparsecs away, which is well over 300 million light years away. And to date, it has over 2,000 member galaxies. So its core is rich and crowded and dynamically complex. Just to give you a sense of scale, this is around about the an image of the Milky Way. You are here, Brownfield, somewhere around there. And to give you some sort of sense of scale, this is how the Milky Way would look in the Coma Cluster. So relating to all the other. So it gives you a sense of perspective, I think. But the objects that I'm looking for, they're globular clusters, okay? And you can see on this, when we zoom in on this very tiny area here, each of those point sources in the magnified image, that is what I was talking about. That's the integrated light from thousands of stars that we see. And they're very, very difficult to pick out. But you can see there are actually thousands of them within that area. So with the HST, those compact stellar systems become measurable as populations. So we can count them, we can map them, we can measure their colors, we can ask how their properties change with the environment. So the final question then becomes, where does this data come from? So this is the data that I've been using for all three papers that I've been working on. All three papers were built on HST, so Hubble Space Telescope, ACS data, active camera surveys, imaging data from the Coma core. And this is from a catalogue of compact stellar systems, which was constructed by my colleague and supervisor, Dr. Madrid, where the globular clusters and the UCDs were selected based on size, morphology, magnitude, and colour. So the key point here is that this gives me the positions, the magnitudes, and the colours and the local spatial structure for more than 23,000 candidate objects. So then the other thing that I had, the other set of data, is a galaxy sample. I produced this from some archives, and I connect the compact stellar systems to a bright galaxy sample in the same region. So the red crosses here, as you can see on the diagram, these are the brighter galaxies from the NGC and IC catalogue. And then other bright galaxies brighter than 19th magnitude make up 173 Coma galaxies with a sample from Sinbad in a region, and the photometry came from the Sloan Digital Sky Survey. So this lets me ask not just where the compact stellar systems are, but also how their numbers, their colors and spatial distributions relate to the galaxy properties and to the local cluster environment. So with that data in place, I now am in a position to move through the 3 lines of evidence, the 3 papers which I've been working on. So firstly, UCDs, ultra compact dwarfs. This paper was concentrating on that. So UCDs are cool because they're from, as I mentioned before, they're 10 to 100 parsecs across, but they've got millions to hundreds of millions of stars within that very, very small area. Some of them are also giant star clusters, and some of them, maybe they've got this sort of dual nature to them. Some of them may be stripped galactic nuclei. And the ones which are galactic nuclei may actually harbour massive black holes as well. So they look like star clusters. They can be as compact as a few tens of parsecs, but some may actually be these surviving nuclei of much larger galaxies, which is indicative of stripping events and environmental processing in itself. So the role of paper 1 in this thesis was to establish the UCD population in the Coma Cluster, as well as the first hints of environmental signatures. And it was published in the Astrophysical Journal, APJ, last year. So what are the highlights from the paper? So the main thing was the identification of over 500 UCD candidates with notable agglomerations around 3 of the giant ellipticals, NGC 4889 and NGC 4874, which are in the middle and the right-hand side of this diagram, this figure. So those 2 galaxies, I should say straight off the mark, those are what we call BCGs. Those are the brightest cluster galaxies. And Coma is actually unusual in so much as it's got 2 galaxies, 2 giant ellipticals, which could be considered brightest cluster galaxies, which I'll refer to from now on as BCGs. And then the other one on the left-hand side is IC 4051, which is unusual in itself. So the agglomerations of UCDs were associated with these, and you can see the spatial distribution there. The other thing I found was that the blue UCDs actually exhibit a much wider spatial distribution than the red UCDs. So this is the point at which I'm starting to talk about colours, and I'm starting to talk about things like metallicity, which actually are used quite a bit throughout this talk. So just for the sake of the non-astronomers in the audience, astronomers have to deal with much complexity, and so we try to simplify things as much as possible. So as a result, everything other than hydrogen and helium we regard as metals. Okay, so the abundance of those elements in stars, galaxies, and other astronomical objects we refer to as the metallicity, and it's important because it affects the color of those objects. So when we talk about a color, this is not just a label; it's something which is a real physical effect. So objects with a higher metallicity tend to be redder, and objects with a lower metallicity tend to be bluer. And this is also true for globular clusters and compact stellar systems in general. So then we move on to in paper 1, and this is one of the key diagnostics which I got from paper 1. Just to explain this figure, this is a color magnitude diagram. Along the bottom you have the color of the compact stellar systems, and then along the vertical axis you have the magnitude. So plotting the color of those like this, and the magnitude against the color, you end up with a kind of Gaussian distribution, and you'll see each of those dots is the integrated light from all of the stars within that population. So these are not individual stars; these are individual compact stellar systems, and we end up with each sorry, the photometry here shows what is a familiar to astronomers red and blue compact stellar system populations. So this is where as I mentioned, the bluer compact stellar systems actually tend to form from metal pore gases, pristine metal pore gases. And the redder compact stellar systems tend to form during later formation episodes where the gases have been contaminated by metal-rich byproducts, say of supernova explosions and so on. So they tend to be redder, and so you get this very much bimodal populations which occur within this type of environment. The thing to note here is what we call the blue tilt. Okay, so the blue line, the blue subpopulation, with increasing magnitudes, which correlates with increasing size, you actually get the blue line moving towards the redder side of the diagram, because the brighter magnitude of compact stellar systems tend to be bigger, so they tend to retain more of their supernova ejecta. So I won't go into this in too much detail, but this is actually quite important for later on for paper 3. Paper 3 actually explores this a little bit further, the colours of the compact stellar systems. Okay, so the next diagnostic in paper 1 was the globular cluster luminosity function. So this is where we plot a count of globular clusters, and this is globular clusters, not just UCDs. We plot a count of globular clusters against magnitude bins. And the important thing here is you can see the histogram of the counts, but then fitting a Gaussian profile to that with its peak at what we would expect to be the peak of the globular cluster luminosity function at the distance of Coma. You can see that there's, taking the difference between the two, there's actually a residual at the bright end. So that then gives us evidence that there is an excess at the bright end, which provides evidence for something more than just large globular clusters as part of this distribution, as part of this this population. So plotting all of the candidates' UCD positions now, and over an SDSS image, so a 2D density map, creating a 2D density map. The red circles on this diagram actually show the extent, and 8 effective radii of all of the galaxies, which I'm considering. And the red circles actually, sorry, the red circles show the extent of the galaxies, varying the size of that circle and counting the number of UCDs and globular clusters in this case on this diagram, counting them and comparing the two for being inside those circles for multiples of the effective radii and outside. You can see there's a distinct difference between the UCDs and the globular clusters. So taking the extent of the galaxy as 8 effective radii, you can see that there's very much a great difference between these two. And the globular clusters are almost twice as likely to be considered intra-cluster via this method than this criteria than the UCDs. So then looking at the color, so splitting by color as we talked about before, and mapping, doing the same spatial distribution for the UCDs against on the SDSS map. You can see that there are notable agglomerations again, which emerge around these 3 giant ellipticals, but the redder UCDs are very much more centrally concentrated around these 3 galaxies, and the blue UCDs, blue UCGs are very much UCDs are very much more spatially distributed than the red ones. So this is indicative. Again, there are differences between these two populations, and they're affected differently. So paper 3 then revisits that for the full globular cluster population. So the implications of paper one. So it focused on the UCD population from a catalogue of 23,000 candidates. There are 500 over 500 UCD candidates identified. I mapped the spatial distribution, and the main results are that UCDs are not randomly distributed, as I mentioned. So they're concentrated around the three giant ellipticals. They also show extended and intracluster structure. So the GCLF shows an excess at the bright end, which suggests a composite population, and there are spatial trends which hint at environmental processing. So you get the brighter, redder UCDs, which are centrally concentrated, and then the dimmer, bluer UCDs, which are spatially distributed and much more likely to be intracluster. So paper one gave me the first indications that compact stellar systems in Coma actually retain the signatures of a turbulent cluster environment, and showed that compact stellar systems are highly structured across the cluster. So the next question was whether individual galaxies have the number of globular clusters that we would expect, whether some systems actually show evidence for depletion, for deficiencies within their globular cluster population. And that in itself would be consistent with a stripping process. And I'm happy to say that this was actually also published in the APJ last month. So in paper two, I highlight several galaxies which do show depleted systems, depleted globular cluster systems, but not all deficits actually look the same. So there's some of them are highly asymmetric, and some of them are much more isotropic. So that distinction actually matters for interpretation. So dropping into the paper, my first indication of deficits was revealed by a visual inspection. So here I'm showing IC 4051 and NGC 4876. So these two galaxies have similar luminosities, but they've actually got drastically different GC densities. So on the left, So on the left, we've got IC 4051, and that's the original ACS image, or a mosaic of two of those images, which it happens to be right in the middle, unfortunately, but you can see the boundary between the two. And then on the right of these two pairs of images, there's galaxy light modeled, and then subtracting that galaxy light from that image, you then end up with the background sources. So I don't know whether you can see those on there or not, but hopefully if I zoom in a little bit, you can see there's a big difference between those two galaxies in terms of their compact stellar system population. So this is an indication these are real, population differences. They're not just photometric effects.
You say background, but they could also be foreground.
Yes. In terms of the background light was subtracted from the galaxy, but yeah, yeah. So then I moved on from the visual inspection and started to do something a little bit more statistical. So I took a Voronoi technique to look at the radial profiles around the BCG. So this is the BCG NGC 4874. The Voronoi technique is good because it's for each of those points of light, you assign an area to it, so you can work out the individual densities associated with that object itself. The other approach to doing radial profiles would be to take an annulus in radius, the type of approach that you would take normally, and then count up all the compact stellar systems within those annuli, and then plot that against the distance. But using the Voronoi technique, you get very much more detail, and it's the annulus approach is kind of a sledgehammer type approach in time. So looking at the dots here, these are all individual the densities of individual compact stellar systems. The dotted line is a circuit fit profile to the annular radial fit. And then taking the difference between those two, you actually get a residual of the radial profile. And smoothing that, you end up with the graph at the bottom. The important thing here is that you've got the smooth profile actually shows up excesses and deficits at points which align with the radial distance of some of those galaxies. So this is the first indication that, for example, NGC 4876, there aren't as many globular clusters, there aren't as many compact stellar systems there. You can see a dip in the profile. And there are excesses for other ones and also offsets associated with some of the other galaxies as well. So this isn't behaving quite how we would expect it to behave. So then taking something called the globular cluster specific frequency, and this is something which gives an empirical relationship between the globular cluster count based on the galaxy visual magnitude. And I used a curve from Eric Peng and calibrated this. So the two curves at the top of this figure, the dotted line at the top is a curve from the globular clusters in the Virgo cluster. Okay, so it's a cluster-based compact stellar system curve of the specific frequency which I've used and then mapped onto the Coma cluster. So assuming this is relatively the right shape of curve, and the specific frequency from Harrison et al. And the dotted line, as I say, is that curve, but including the BCGs. The orange line is just using the bulk of the galaxies without the BCGs, so going through the majority of the galaxies. So either way, there's a difference between the Coma cluster and the galaxies within the Coma cluster and this calibration, this specific frequency calibrated curve. Yes, there's a lot of scatter on it, but the specific frequency is not behaving like a simple host luminosity scaling for the Coma core. So looking at all these, you see these upper limits here. The orange ones are upper limits where there's not enough data, there's not enough compact stellar systems within those areas. So these are all much lower than we would expect for the compact stellar system. So I then developed that technique further, and did a simulation. So effectively, this is saying, okay, using the specific frequency, what would I expect for the spatial distribution around each of these galaxies? And then mapping that and comparing it with the actual data, so observed minus actual, end up with a residual, and then take a significance map. So the significance essentially scales the residual on the basis of the uncertainty in that result. Sorry, the confidence interval in that result. So that just gives us, whether the areas here are significant or not. So you can see that there are areas where there are deficits. There are areas where there are far more than we would expect. Certainly around, for example, NGC 4876, which is the galaxy that we looked at before, without that whole population that we saw visually. So this is for statistical confirmation of that. Mm-hmm. So then looking at the asymmetry of some of the galaxies, or all of these galaxies. So this is doing an azimuthal asymmetry on each of these galaxies. You can see, for example, here around the BCG NGC 4874, we've got. We always have that problem. So this is IC 3998, NGC 4876, our old friend we've seen a couple of times, and NGC 4875. So those are galaxies which are highly asymmetric, as shown by the magnitude of this pointy line here, the magnitude line, but they're all significantly, they're pointing towards the BCG, which is really a smoking gun with regards to the fact that they've been interacting with the gravitational potential of that BCG. There are other galaxies as well which show moderate symmetries. So, for example, MGC 4883, and also there are some which are isotropic. There's some which have no asymmetry at all, but also have deficits. So the geometry actually matters. So paper 2, implications. So not only do some galaxies actually have fewer globular clusters than we would expect, also the geometry matters. The geometry matters for the interpretation. Some systems are asymmetric, which is consistent with recent or ongoing stripping, and other systems are isotropic, which may reflect either older phase mixing, pre-processing, symmetric truncation, or intrinsically low GC formation efficiency in the first place. So the broader point here is that the globular cluster specific frequency is fragile in the Coma core, in that cluster environment. It's not simply a property of the galaxy, but it's also a record of the environmental processing within that cluster environment. So then moving on to paper 3, I am hurrying now on the time. Moving on to paper 3, Paper 2 asked whether galaxies have the expected number of globular clusters, and paper 3 takes that further and asks whether the composition of those globular cluster systems, especially the balance of the blue and red populations, also changes with environment. So this is the final paper, and has just been submitted to the APJ and is currently under review. So the highlights of paper 3, globular cluster color distribution varies, but it's not fully explained by the canonical host mass metallicity relation. Upon examining further and investigating further, I actually found that there's a structured environment. It's not radially symmetric about the cluster center, and the strongest trends that we see of the color distribution are actually with the local globular cluster density. And the blue globular clusters are especially sensitive to this redistribution and environmental processing. So when thinking about motivation, we recall the color magnitude diagram that I made in paper 1. And the reason color matters here, as I mentioned before, just to remind you, globular cluster color is a proxy for metallicity and population history. So the blue and red globular clusters trace different structural components of a galaxy based on the fact that the red globular clusters are generally more metal rich and centrally concentrated around the galaxy, while the blue globular clusters are more metal poor and spatially distributed. So if the dense environments strip the outskirts of a galaxy first, then the blue globular cluster population should be especially sensitive to that processing. So this figure shows, this is going to take a little bit of explaining. So I started out by looking at the median globular cluster color, which I'm taking to mean all of the globular clusters within 8 effective radii of a galaxy, and then taking the median of that color to be the GCS, the globular cluster system color, if you see what I mean. So taking that median globular cluster color and plotting it against the host galaxy color, that's the figure at the top there, the panel at the top, and that shows there is maybe a little bit of relationship there. What I also looked at was the median globular cluster color and the host galaxy luminosity. So the host galaxy visual luminosity, which is the middle panel there, and there's a recognized relationship between those two things. So taking that out, regressing that, gives me the graph at the bottom. And this is important then because effectively it's saying, yes, the median globular cluster color broadly follows the host galaxy color and luminosity, as we would expect from the mass metallicity relationship. But there's real residual scatter here. And I've named some of the galaxies which appear later in the dissertation. But paper 3 asked whether that scatter then is just noise or whether it contains environmental information, something that we can glean from environmental analysis. So how do I do that? So the diagnostic that I use in paper 3 is the blue globular cluster fraction excess. So this is, I refer to this throughout as delta FB. So the idea is simple. For each galaxy, I ask whether it contains more or fewer blue globular clusters than expected. So within that population, is it higher or lower than expected? The positive delta FB would actually mean that the galaxy has an excess blue globular cluster population, and a negative delta FB means it would be redder than expected, or equivalently deficient in blue globular clusters. So as we've already noted, the blue globular clusters generally occupy the outer parts of galaxy halos, making them especially sensitive to stripping and redistribution. So I note here that I don't classify each object simply as blue or red. I assign a probability of it belonging to the blue component. And then that's actually based on the fixed Coma wide mixture model, which was taken from the color magnitude diagram that I produced in paper 1. And that gives me then a background corrected mean blue contribution for each galaxy. From these figures, so the distribution is for the histogram is for each individual galaxy, and then the curves are the Coma reference model which I've used. So you can see from these figures that the blue GC fraction, the delta FB, is not just an abstract number; it's a real thing. The median offset to the left of the distribution peak means it's a blue excess, and to the right means there's a red excess. So I'm examining this for each of the galaxies within the Coma cluster, and then mapping that against environmental metrics. So, for example, how far away is it from the BCG midpoint? So I tested the delta FB and environmental metrics on several scales. So cluster centric radius, BCG proximity, BCG tidal proxy, and local globular cluster density as well. So the cluster centric trends, which are shown here, for what I take to be the fiducial center of the cluster, the BCG midpoint, are present, but these relationships are also sensitive to how the cluster center is defined. And that in itself is a clue that Coma is not simply a spherically symmetric environment. So the strongest trend, though, emerges with delta FB against the local globular cluster density. So you can see, again, there are some named galaxies here. You can see NGC 4876 down here, our old friend. And on this plot, you can see that as you move towards higher local density, which is towards the right of the plot, delta FB becomes more negative. So effectively, this means that the higher local globular cluster density tend to have redder residual GC populations, or equivalently blue GC deficits. So then adapting my code for asymmetry, which I used in paper 2 to take on the probability values, I tested whether the blue GC fraction excess is related to the spatial asymmetry of the globular cluster systems. And I found that galaxies with stronger asymmetry tends to have more negative delta FB, which means that more asymmetric systems tend to have redder globular cluster excesses. And the strongest correlation is actually with the blue weighted asymmetry, but the total and red asymmetries are also significant. So to summarize paper 3, I noted that not all differences in globular cluster distribution are explained in relation to their host galaxies, to the host galaxy mass or color. And investigating these differences, I found that there are trends on multiple scales, so cluster-wide scales, BCG level scales, and local level as well. And I found that the strongest trend is actually emerging between the blue globular cluster fraction excess and the local globular cluster density. I also found that the populations of blue globular clusters are much more sensitive to their environment, which is consistent with the stripping and redistribution of the more loosely bound outer halo components. So now we've seen the summary results for the 3 papers, I'll now bring those results together into the broader physical interpretation. So just to remind you, paper 1 showed that the UCD population our populations are potentially composite, forming through multiple pathways. They also show evidence for spatial structure in their color distribution. Paper 2 provided evidence that some galaxies have depleted globular cluster systems with a range of asymmetries. And paper 3 showed that the globular cluster color distribution changes with the environment, but on multiple scales. So what I found is evidence for a structured multi-scale environment within the Coma cluster. This environment is recorded by the populations of compact stellar systems hosted by each galaxy. The environmental signal is not dominated by a single smooth radial profile. Instead, it appears across multiple scales. So there's the broader cluster environment, the dual BCG structure, and then the local density field as well. But what about the preferential response of the blue globular clusters? Well, because they're distributed over much larger galactocentric radii, the blue globular clusters are more vulnerable to stripping and redistribution. And asymmetry and stripping geometry, well, the deficits are not just counts. So asymmetric deficits may indicate recent or ongoing stripping, while more isotropic deficits could reflect older phase mix stripping, symmetric truncation, or intrinsically globular cluster poor populations. So bringing this all together, this schematic shows the physical picture suggested by this thesis. The top row is the structured Coma environment, a global cluster potential, the dual BCG core around NGC 4874, NGC 4889, and local galaxy and GC density substructure. The key point is that Coma is not simply a smooth radially symmetric environment. And the middle row shows the physical processes that can act in that environment. So, for example, the outer blue globular cluster populations may be preferentially stripped, redistributed, and eventually phase mixed into the cluster environment at the same time. And some of the UCDs may be linked to the disruption of nucleated dwarfs. And the bottom row finally shows the observable outcomes, the observable consequences, if you like, the altered globular cluster color distributions, globular cluster deficits and asymmetries, near isotropic deficits after phase mixing, enhanced local or intracluster GC density, and then the bright end excess or UCD contributions as well. So The thesis level interpretation is that these signatures are connected. Compact stellar systems preserve measurable evidence for how galaxies in the Coma core have been stripped, redistributed, and environmentally processed. But what about the future? Well, integral field and multi-object spectroscopy facilities such as MUSE on the VLT, so the multi-unit spectroscopic explorer, and in the longer term, the extra large 30-meter class telescopes such as the Giant Magellan Telescope and 30-meter telescope will make it possible to extend globular cluster and UCD spectroscopy to fainter compact stellar systems in Coma, improving the completeness of the surveyed populations. Wide field imaging of the Euclid and Nancy Grace Roman space telescopes will provide contiguous and homogeneous coverage over much larger areas than the 26 individual multi-epoch mosaic that the HST and ACS as used in this thesis. And this is exciting as it will allow connection of the resolved Coma core measurements of in this thesis to a full cluster scale environment, as I've only looked at the Coma core, and to extend that out would be fantastic. So finally, to use cosmological simulations to model globular clusters and ultra-compact dwarf populations in cluster environments would allow testing of whether depleted globular cluster system, blue fraction variations, overdensities, asymmetries, whether they all arise naturally from tidal stripping, from pre-processing and phase mixing within those cluster environments. So in conclusion, compact stellar systems trace environmental processing in Coma through several complementary signatures. Firstly, the UCDs are a composite population. Some may represent high mass end of the GC population, while others could be connected to environmental processing. They also show spatial structure with bluer ultra-compact dwarfs more broadly distributed and more closely linked to the cluster environment. Secondly, the GC systems of individual galaxies show depletion, overdensities, and asymmetries, and these provide evidence for stripping and redistribution, either into other galaxy halos or into the intracluster environment. The geometry also matters. Asymmetric systems are more consistent with more recent or ongoing interaction, while more symmetric deficits may reflect older phase mixed processing. And finally, the GC color distribution changes with the environment. Deficits in the blue globular cluster fraction most strongly trace the local density of globular clusters, showing that GC color distributions retain information about environmental history. So the big picture is that Coma is not a smooth, spherically symmetric environment. Its compact stellar systems record structure on several scales: the broader cluster potential, dual BCG core, and local density substructure. They also record the stripping and redistribution of galaxy halos. And across this thesis, these signatures appear in different ways. UCD populations are spatially structured. Some globular cluster systems show depletion and asymmetry, and GC color distributions vary with the environment. Together, these results show that compact stellar systems preserve a fossil record of environmental processing within the Coma core. So that's the central conclusion of this work. Compact stellar systems are not just small companions to galaxies. They're long-lived traces of how galaxies evolve in dense cluster environments. Thank you very much. Those are the
Well, thank you, Richard. This is great. So we have time for questions from the public. I will let you handle any questions from BiNAB, Richard. And
yeah, sure, okay. Go for it.
A couple of questions. So first paper, you're talking about how the ultra compact dwarfs have the composite red and blue subpopulations.
Yes, yeah.
And then in paper 3, you're talking about red and blue subpopulations of globular clusters.
Yeah.
Are you saying that would you say the ultra compact dwarfs are respectively continuous with their globular clusters, or that one of the populations of UCDs is a continuum with the globular clusters, or they have completely different formation mechanisms?
So the point with the ultra compact dwarfs is that they do have this dual nature. They are a composite population. Some of them are big globular clusters, so it's just a classification thing. So they are the top end, the bigger globular clusters. But then there's this dual nature comes from the fact that when you get, say, dwarf galaxies or nucleated dwarf galaxies, if the galaxy is processed within a cluster environment and the outer layers are stripped off, that nucleus then looks exactly like a UCD. So it has the same size, mass range, and it has the same brightness characteristics as a grown globular cluster. So you need other information then in order to determine whether it's what the formation mechanism was.
So you're saying one population of UCDs is basically the tail of the globular cluster, and the other is basically a type of dwarf elliptical. That's separate.
Exactly. But it's been processed.
Processed.
Exactly. Yeah.
And which is which, the red or the blue?
So they both have red and blue components to them.
Okay. All right.
Yeah.
What about the isotropic clusters? Can you say anything definitive about their past, or it's impossible to do that?
So that's a good question. That's a key question. The fact that they're isotropic, it's very difficult to then say, are they intrinsically GC poor, or have they been processed a long time ago? And then as they're coming, once they come into the cluster, because it's happened a long time ago, they've had time to mix, and it's the population has time to settle around the galaxy, so it loses that asymmetry.
Yeah, no, I mean, is there any trace of that? I mean, do they leave any trace before being isotropic, or like their environment, like their surrounding kind of thing? Can you say anything from that, or is just not
the fact that they're isotropic? I don't think so. No, I mean it's difficult to say and sort of glean any further information than that. I think as I mentioned, one of the key things is spectroscopic information, which you could it's very difficult, certainly at the distance of Coma, to get that information because you don't get the light from those things. It's very difficult to then determine specific membership of these things and associate them with a specific galaxy, which is why I assigned a probability to these clusters, to the compact stellar systems, because you can't say for definite it's associated with this galaxy or not. So it's just a probability associated with it.
Thank you.
Yes.
Somewhere in the area of the first paper, you subtract the bright source from foreground or background, whatever it is, and you arrive at this granular population in the background.
Yes.
Just a technical question: do you know what the resolution / color / intensity resolution of the images is that you look at? Because you kind of obviously cannot be saturated, but then you have to have enough, resolution in your intensity to be able to see the little specks when you take off the more or less unified main source out of it.
Yeah, I mean that's I'm not quite sure what the question is there.
Well,
so it's kind of
dynamic range, how many bits?
The dynamic range, yeah. So these are ACS images, so the raw data is effectively it's electrons, so you get counts per second of the from the original data, and so they're CCD type images, and so in terms of the dynamic range, they go from
So it's an integer, but there's no limit on the size of the
yeah,
integer.
exactly. Yeah. So you can there's quite a range there.
Yeah.
And there are tools to use to do that. So source extraction, the tools are quite mature in that respect. Been around for 20, 30 years. Yeah, thanks.
16 billion inches.
Okay, that's okay, but not great.
Okay, we have time to, yeah.
How did you distinguish how do you categorize blue and red with metal, you say deficiency and metal reach? How do you distinguish that?
In what way? So I used in the third paper where I'm defining the blue probability.
In one of the graph, like kind of Gaussian, blue and red.
This one?
Yes.
Yeah. That's a good question, actually. So the way that this works is you can see from this figure that the blue and the red population are actually they're actually visually blended. Now, ordinarily, if for a closer cluster like Virgo or Fornax or something like that, you would be able to see two distinct Gaussians which emerge, which gives you a big indication that you've got these two populations here. So they would be physically separated. Here, I had to do a Gaussian mixed model. So doing a bimodal fitting of the two Gaussians and making sure that the bimodal solution is better than a unimodal solution, effectively. And then splitting those into, you can see the wiggly lines here, splitting those into different magnitude bins where I've got the sufficient data coming through, then gives you a best fit on these lines to be able to say, yeah, actually the bimodal solution is better, and the best fit line then is that.
And is the best fit line for the red assumed to have no slope, or it just happened to be nearly vertical?
So I assume that has no slope. Yes, that is a vertical fit. You can see there is a slight tilt, just at the top. But that's when I'm running out of data. So in the middle part, sort of 26 to 24 magnitude, that's where the majority of the data is.
Was that a Bayesian hypothesis test between the two different types of model, or what? How did you distinguish between the bimodal and?
I think it was just a chi-square, something like that. So,
Like I have a very, very naive question because I'm not into this field, so like I'm trying to understand.
There's no such thing as a bad question.
So like in a typical set of clusters, or are there more asymmetric ones or symmetric ones?
In terms of the
population.
In terms of the GCS?
Yep, let's say yeah.
Yeah. So that's a good question. I think from memory, because I only inspected the galaxies which had deficits on them. So that's a good question, and that would be something which would be worthwhile exploring. I think most of the galaxies though they seem to be more isotropic. They seem to be more symmetric than there's the galaxies, and doing the asymmetry testing, there were only a few that came out as very, very strongly asymmetric. There's a few medium, moderate asymmetries associated with them as well, and there's some isotropic systems. So there is a range, but the strongly asymmetric systems are definitely far and few between.
Okay. Well, thank you for all these great questions, everyone, and thank you for being here. I think it is 3 p.m., so it is time to end the public section of the meeting. I'm told that some refreshments will be served in Bainab at around 2:30 p.m. Texas time. So if you have time, and you can wait for them just outside. And now it's time for the committee to get together. So
Thank you. I enjoyed it very much.
Thank you. Congratulations.
Yeah. You want to stop the recording?
we can also stop the recording.
Sure. We'll do that. Are we asking questions to Richard?